Design assignment 2, not possible. Last time also we have extended. That time itself, the office people said that it's not possible to extend beyond this point because they will do the evaluation for all the marks by tomorrow. So it's not possible, it seems. Okay. So this week we'll be seeing some of the important concepts in state space domain. We've been telling there are two domains, the time and frequency. Similarly, we have also seen different aspects based on transfer function representation. Now we are seeing systems that's being represented in state space form. So these are different kinds of representations, right? So out of this, in the transfer function based analysis, we have seen time response, frequency response based, right? So here, state space is it is mostly it will be in continuous and discrete form. These both are not completely equivalent. These are different kinds of representation in different domains. Right. You know the common state space format, right? X dot equal to AX plus BU, Y equal to CX, where this X dot represents the change in state or rate of change of state, like how the state is being propagated over a time period, where this X is the actual state representation and this Y is the control input, control input, whereas this A A represents the state transition matrix and B represents the control input matrix. And here C it's a output matrix. Again, hex is a state, both same state that we used here. Both are same. So this state space representation tells us the relation between your state, your input, and your output of a system. So in transfer function, it will be Laplace of output by Laplace of input, where here it will tell a relationship between an input to system. So what output it is giving. This is one form of representation. This is the another form of representation representing the same system. You can represent the same RLC circuit in either transfer function or state space form. Same RC circuit or any mass spring damper system in state space form and the transfer function form. But when compared to transfer function with respect to state space is more flexible that you can use it for the higher order system, wherein doing that for a with the transfer function is difficult because transfer function represent the relation between one input to one output. If you want to represent two inputs, for example, I have an input 1, input 2 for a system, so that I'm getting output 1 and output 2. We don't know the relation between this with the transfer function. If you want to write this in a transfer function, you would need four different transfer functions. For example, Laplace of output 1 by output 2, Laplace of input 1. Similarly, Laplace of output 1 by input 2, Laplace of output 2 by input 1, and output 2 by input 2. So it's four different transfer functions you would need in case of representing the same system in transfer function. Whereas you can represent this in terms of a 2 cross 2 matrix in a state space representation. That's why I'm saying state space is more flexible than transfer function. But for simple systems like first order, second order, up to third order systems, you may use transfer function because using Laplace we'll be able to get it very quickly. And for state space, you would need a dynamic equation or the relation between it properly so that you can derive it from nth order equation to n single order equations. Right. So far you have seen all these things. Just to warm up, I have told this. Chakravarti would have taken controllability, observability until then, I hope. So then we will move towards the controller design in state space representation. So in transfer function representation, the most functional controller you used is a PID control, right? So in PID control, you would need a KI by S or a KDS or KP, something. P, I, and D controllers you have used, mix and match, whatever based on the requirements you used in the transfer function representation. So for if you closely look into this PID controller information, what you are actually doing is, if I have a system like this S plus A and I put a PID controller here KI by S or a PD controller here KD into S, I am actually increasing the zero, that is a numerator, or increasing the pole, right? So I have a system that has a minus A, but by including a controller like I or a D, I am placing another pole at origin. In the case of I am placing one pole at origin. In the case of D, I am placing one pole at the 1 0 at the origin. So that's how we use a PID controller. So based on this information, we are influencing the system to work according to our desired specifications. How we would have told us, maybe this is my original output and I don't want this big overshoot, so I am putting a integral controller. So I am trying to reduce, sorry, I'm putting a derivative controller and trying to bring this overshoot down, but the system will be little slower compared to the other system. So by placing a pole or a zero, we are manipulating the output of a system so that it will behave according to our requirement. That is the same thing we are going to do in state space analysis also, but we are keeping a name called pole placement controller. So instead of adding a pole at a origin, we are going to keep poles wherever we need so that we will get the desired location. That's what we are going to do in this pole placement analysis. Any doubt in the introduction? Why we need, what is the necessity of it? Okay. Why we call this as a pole placement controller or pole location? Why are we changing the pole location? So if you consider your transfer function, sorry, state space equation of a system, so the natural function of the system is governed by this A matrix, because this A matrix holds all the information about your states. For example, I have a state that is my x is equal to position and a velocity. Then the matrix that holds 1, 2, 3, 4 for this position and velocity holds the information about my states. So this is the powerhouse or cell that power of the cell that holds the information, right? So I would say this will be 1p plus 2v 3p plus 4v, kind of I will get to know the coefficients or the energy in terms of physics or power, whatever you like to equate it to. So that's how it stores the information. So how can we relate this to the thing that we already studied? For example, in your time response analysis, so if you have a second order system, right? Second order system will look something like this: s square plus 2 zeta omega n s plus omega n square. I'm trying to teach this via the thing that we already know. It will be easy. So if you see this, you will say zeta is my damping ratio and omega n is the frequency of oscillation. So this zeta will decide how much overshoot my system is going to have. If my zeta is nearly 0 to minus 1, 0 to 1, I have a nominal overshoot and I have a more settling time. And this omega n decides how much is the frequency of the oscillations. That is how we define a second order system in a transfer function representation. If you find the pole, this is the characteristic equation, right? If I equate the denominator to 0, then I would get a characteristic equation. And from this I will find the pole. If you remember, our poles will be like something like this: zeta omega n plus or minus j omega n root of 1 minus zeta square. That is how our poles will be. So when you find a settling time, that is around 4 by zeta omega n, and your peak overshoot will be something like this: zeta pi root of 1 minus zeta square. So for all the time response or performance related problems, your zeta and omega n played a major role, where that the same thing that is playing a role in your pole location, poles of the system. So similarly, in a state space equation, so this is the pole of the transfer function denominator, that is a characteristic equation. So similarly, for a state space equation, or a state space representation, the poles of a system is equal to eigenvalues of its system state matrix, state transition matrix or system matrix, whatever you call it, that is A. So how will you find the poles of a system when I give a state space representation? X dot is equal to Ax plus Bu. So I will just find the eigenvalues of A, that will give the poles of the system. So for a 2 cross 2 matrix, what are the number of poles you will get? Can you type it in the chat box? For a 2 cross 2 matrix, how many poles or how many roots you will get? 2 roots. Very good. For a 4 cross 4 matrix, you'll get 4 roots, right? So just you have to find the eigenvalues of the A matrix, then you will get the poles of the system. From the poles, you will say whether the system is stable or not. Stable or unstable, right? So similarly to transfer function, we would see real values of poles. If it is less than 0, then it is stable. If it is okay. If the real of poles greater than 0, then it is unstable. If it is equal to 0, it is marginally stable. So for this, have you done the linear algebra course? Anybody who didn't give linear algebra course? Can you raise your hand, or somehow you can show to me? You know linear algebra, right? Eigenvalues, eigenvectors. Yes. Okay, it was in math too. Thank you. Okay. So by seeing this, would you be able to tell what is the eigenvalue of this matrix? If you can recollect. Oh, nice.
1 1.
1 1, right? Because this is a triangular matrix. For triangular matrix, the diagonals are the eigenvalues of the matrix. Okay, good. So similar to that, if it is a like full matrix, then you can find it using lambda I minus a equal to 0, where you can replace lambda 0 0 lambda and minus 1 2 3 4. By doing this and equating it to 0, you will have a characteristic equation. Out of this, you will find the roots of the system, that is the eigenvalue of the system. Okay. So there might be problems that you would be asked to find the poles of the system with that state space representation. In that case, you have to find the eigenvalues, and then you have to check whether it is like negative, that is less than 0 or greater than 0, and you have to say whether it is stable or unstable. Any doubt in this type? Can you do this type of problem? I'll do an example, but with the understanding I'm asking.
No, yes, ma'am.
Okay, fine. Right. Then Jada would have thought about the controllability and observability matrix. This is another important concepts in state space equations. So why we see this is for studying the pole placement, you need this basics. So this tells whether the system is controllable or not. For example, even leave all the mathematical concepts or any technical things. If I want to control my car, I should know or I should be able to hold my steering, right? If I take out the steering from the car, how will you control your car? How will you control the steering of your car? So the basic necessary equation or necessary thing for any system to be to design a controller for any system, it should be controllable. That's what this controllability and observability is telling. So observability comes in a way. uh, this help us define. Wait, I'm trying to make it simple. Let me know if you didn't understand this. Controllability helps us to design a controller. Observability helps us to design a observer. Okay. So controller we know. So if any system is there, I'm giving an input, getting an output, and sometimes I will use only the feedback control, that is taking an output and giving it back to the system. That is a simple closed loop control. Otherwise, I will put another person here who is called as feedback or H. By changing this, we will control the system. This is also called as a general closed loop control. So without, if I keep this as one constant, then it is unity feedback. If I keep some other value that is not equal to one, then it is a standard feedback control, standard closed loop control, not feedback control. So in feedback control, state feedback control, what we used to do is we will do u equal to minus k into x. Instead of h that we used to do as a constant, we will put a controller k that can be constant or that can be a matrix. Okay. General feedback control will have only the constant matrix. Please give me some 2-3 minutes. Okay. I'll be back. Sorry, there was some building inspection. Okay, so we've been speaking about this, right? So the feedback or a state feedback controller is simply replacing the constant with the matrix. So matrix can be anything K1, K2 based on the order of your system that goes along with your state space matrix. If your matrix holds 2 cross 2, then this will also be 2 cross 1, something like that. Otherwise, if your matrix has n cross n, this will be n cross 1 kind of. So that is the controller we are defining for a control aspect to make your system give your desired response. To make sure you can design this type of controller, you should know whether the system is controllable. That purpose have been done using this controllability matrix. So if the controllability matrix for any system has a full rank or it is controllable, then we can design a controller. Similarly, we can put the observer. Where the observer comes into places, in general, students tend to understand controller better than observer because it varies slightly, but still they used to have doubts in this. So if you have a car, for example, this car is traveling along a pathway, and all of a sudden, the tunnel. Okay, it's a closed tunnel, and the car has a GPS. It used to give information about its position, X and Y position, to someone in a controller room where the car has been maybe consider this as a Ola Uber. So it is giving information to the person who booked the cab. So it keeps on coming, and the person used to get the location about the car. But once it enters into the tunnel, it lost its GPS ability. So the car cannot give information about its location whenever it is traveling from this point A to point B. Let's take it takes around 15 minutes to travel through this tunnel. So the during this period, this person might not know that that the car is traveling inside the tunnel. That's why it got lost. They might think that there is some issue with the booking, so it got cancelled or it got stuck. So they want to reset it. So this is a problem when it comes to a controller based or any open loop or anything without an observer. So there comes the observer comes in practice. So observer, you can think this observer as a person who is sitting and monitoring things in the system. For example, you have this system and I have this controller, I have this plant, and I also have a feedback K like this. So here I will have another person in the loop that is called an observer. So this observer will tell the system about the estimate of its positions. All the states, all the estimates of the states. Here the state is a position, so we are estimating the position. So in general, observer estimates the state and update the function or the system using the estimated information whenever the actual information is not available. Clear? So if I have a rocket and I'm ready to launch, there is a fire here, I'm ready to launch, but I should know the temperature inside the rocket, right? If I want to do a temperature inside the rocket, there are many sensors that is available in the market. For a test scenario, I'm saying I don't have much good temperature sensor that can put inside this missile. Okay, it may melt. Whatever temperature I design may melt for that temperature, so I cannot use any temperature outside. So I am putting an observer outside from with the outside temperature and the time it takes to go to the particular point or a breaking point. I can estimate the temperature from outside, which is the work of a observer here. So this observability matrix tells whether it is observable or not in the first place. So if the system is observable, then you can design an observer. If the system is controllable, then you can design a controller. Clear? Any doubt in this?
No, ma'am.
Okay, fine. So why this is necessary? If the I'm saying that I'm designing a controller, right? Basically, what I'm doing, as I explained here, I am moving a poles, right? I'm moving the poles of a system to some point so that I will get the desired location. This controllability tells that you cannot get to access the poles. That is what it is telling. So if the controllability is not there, there is no, it's not controllable, then you cannot move this pole so that you cannot design a controller. So if it is controllable, you can get to access the poles, you can move it around so that you can get a desired output or desired specification. That's why it is important. And other things are post zero cancellations may occur. Transfer functions only reflects controllable part. And there are many things like even a single system can be controllable, not observable, but both controllable and observable, neither controllable nor observable, or observable but controllable. All these combinations can exist for any system. Okay, you cannot assume one thing with the other. You have to check individually whether it is controllable or observable, right? Now we are going to see the state feedback control. I have given a gist about this already. So I'm keeping, this is my plant, the or system, input, output. It's a simple control where I have H to this. So if I replace this H and I with u, that is equivalent to k into x, where this is the x is your system state, right? So you are taking y, that is a combination of c into x from your state space equation, because x dot is equal to ax and y equal to cx, right? Ax plus bu, y equal to cx. If y is the output, then it holds the information about cx. So you are taking cx back and you are multiplying it with the k, and there is a sign negative. So the overall input here u will be minus k into x. So here instead of k, you are replacing it with, instead of h, you are replacing it with k, right? So it's basically you are taking the state back to the system, but with the multiplied version of it, scaled version of it, for example, based on your system vector. So if my system x vector is 2 cross 2, then this will be a 2 cross 2, right? Sorry. If it is 2 cross 2, this should be 2 cross 1. No, 1 cross 2, right? Then only the inner product will be applicable. Then here I have introduced a mistake. Okay. It should be 1 cross 2. If it is n cross n, this should be 1 cross n. Your K matrix will be 1 cross n. Now, our idea is to find the K matrix. How we can find the K matrix? That's what we are trying to see. So, in general, your state space matrix will look like this: Ax plus Bu, y equal to Cx. When I put u equal to minus kx, I'm going to substitute here. Then it will become x dot equal to ax plus b into minus kx into y equal to cx. That won't change. Then the x dot equation becomes a minus bk into x plus b. A minus bk has been gone, right? Only a minus bk, nothing else here. Y equal to Cx. So this is the overall state space matrix after introducing a state feedback control. So your matrix, state transition matrix will become A to A minus Bk naturally. This is the actual system when you implement your control values. So if you want to see whether the overall state feedback closed loop or system control system is stable or not, you have to find the eigenvalues of A minus Bk. If this system is, if this is less than 0, then the closed loop system is stable. Otherwise, the closed loop system is unstable. Okay. We'll solve some problems in this. Okay. Okay, we'll solve as comprehension type so that I can cover all the topics. Consider a system given below. X1 dot x2 dot is equal to x2 plus u square minus x1 plus 5 into 1 minus x1 square into x2 plus u. First question is to find the equilibrium point of the system. You know what is equilibrium point, right? How to find the equilibrium point of a system?
Yes, ma'am.
Okay. So if you have a bowl and I'm dropping a piece inside, so it will go like this, and ultimately it settles down. Why it is settling at the bottom of the bowl? Because it is a curved space and the minima keeps decreasing until it reaches the lowest point of the bowl. That is the minima, local minima of the system. So that's where it settles. So the equilibrium points comes when the system or the state movement is nil. For example, at x1 the position will be here, at x2 it will be here, x3, x4, x5, x6, x7, x8, x9. At some point around xn it will be settled. So if I find a difference between x1 to x2, there will be some point. Similarly, x2 minus x3, there will be something. When I come to find xn minus xn plus 1, then it will be 0. So that's where we have to find the equilibrium point. That's why we are equating x dot d by dt of x1 dot, that is equivalent to 0. So this is where you will find the equilibrium point. So whenever it got settled, there is no movement in between its previous and the next state. That's why we are doing that. This gives you the equilibrium point. So now we are finding the equilibrium point. So if your system has a u and you are asking to find the equilibrium point, you can nullify the input. You can basically put wherever u is, you can put to 0. So it will become, it's like autonomous system without any input. X1 plus 5 into 1 minus x1 square into x2. That's what their entire system is. So if I do x1 dot equal to 0 and x2 dot equal to 0, then I will get x2 equal to 0 and minus x1 plus 5 into 1 minus x1 square into x2 equal to 0. So ultimately x2 equal to 0. So substituting this here, this will give me minus x1 equal to 0. So the equilibrium point is x1 comma x2 equal to 0 comma 0 is my equilibrium point. Only at the origin this will be stable. Sorry, this will be settling, not stable. Any equilibrium point can be stable or unstable, that we have to find. You cannot say equilibrium points are stable. Okay, this at the origin it is settling. So that's why we are calling it as equilibrium point. So the answer for this question is 0 comma 0, right? So I'm marking the equilibrium point as x star to identify it 0 comma 0, where your x is the actual state. Now the second question is asking us to linearize the system around its equilibrium point with u equal to 0 to get, somebody messaged anything, equate it with 0. Yeah, every time you have to equate this to 0. Your x dot equal to 0, your x2 dot equal to 0. Okay, and this is actually dx by dt. That is again dx1 dot. Either it is x1 dot or dx1 by dt. Okay, why we are equating it to 0 is the explanation I have given here. There should not be any change between its successive states. So then it is meaning that it is settled. So that is where we find the equilibrium point. Every time you have to equate it to 0. But every time 0 comma 0 alone won't be the equilibrium point. You have to do properly. So if the x2 is always 0 based on this equation, that's why I'm equating it here. If x2 has two possibilities, you have to find by putting two possibilities also. For when x2 equal to 0, what is x1? For x2 equal to something else, what is x1? So you will get a two set of equilibrium points, 0 comma 0 kind of. So that is based on the system's representation. For this system, only 0 comma 0 is the equilibrium point. No, nothing other can do, because only one possibility is here from this equation we formed, right? Okay. I hope that is clear to you. To get matrix A and B. Okay. Now, how can we linearize a system? You you used to do Jacobian matrix. You can do both Taylor series also. Jacobian is comparatively easy for a state space representation. So for this, sorry, to find the linearized version, I am rewriting the A. A, what is A? X2. Then it is 0 comma 1. Because how I write 0 comma 1 is, let me write it here also. Wait, let me do two steps. A is x2, and they have already told to put y to u equal to 1 minus x1. So I'm putting u equal to 1 plus 5 into x minus 1 minus x1 square into x2. Okay. So now I'm writing in terms of numbers. Then there is no x1, so 0. Only x2, that the coefficient of x2 is 1, like this. So it will be 0 into x1, 1 into x2. Then for this, it will be minus 1, minus 5, it will be, we cannot write like this, right? It's not a linearized version. We have to first linearize it. Okay, sorry. First, we will linearize it. How we will do that? We will write a Jacobian matrix. Dou A by dou x1, dou A by dou x2, maybe not dou A. So x1 dot, right? x1 dot equal x2 dot equal to A into this matrix is A, not it is A equal to. So this matrix. So x1 dot x2 dot. So I'm writing dou x1 dot by dou x1, dou x1 dot by dou x2, dou x2 dot by dou x1, dou x2 dot by dou x2. Is it right? Like sometimes I used to make mistakes. X1 dot should be here or here.
Ma'am, it is right.
It's right, right? Okay, fine. Sometimes I used to write dou x2 dot by dou x1, dou x2 here. So be aware. So the function name should be similar at the top, and this should be similar at the bottom. The state should be similar at the bottom. That's how you write it as Jacobian matrix. Okay. So if I differentiate x1 dot, there is no x1 value, so it will be 0. If I differentiate x2 dot, it will be 1.
Ma'am, first one is del x2 by.
See, okay. This should be x1.
Yes, ma'am.
Okay, fine. Right. Fine. So the first thing is I'm differentiating x1 dot here. I'm differentiating x1 dot this row by x1. That is 0. There is no x1 term. Again, I'm differentiating the same row with x2. That is x2. The coefficient of x2 is 1. Now I'm differentiating the second row x2 dot by x1. So it will give me -1 and minus it will be. Okay, I will rewrite it. Minus x1 plus 5 minus 5 x1 square x2. So this will give me -5. This will go, okay, for x1 it will be there. No? This is minus x1 plus 5 minus 5 x1 square x2. So differentiating this with respect to x1 will give me -1 minus 5, sorry, 10 x1 x2, right? This equation, this is second row equation. Again, differentiating this with respect to x2 give me minus 5 x1 square, right? Now I am replacing x1 comma x2 equal to 0 comma 0. So this is how you linearize around the equilibrium point. Since this is the equilibrium point, you are substituting the equilibrium points back to that. So this will give me 0, 1, -1, 0. We written it right. This is 5x2, no? So this will give me 5. So this is my Jacobian matrix. Actually, this is the linearist version of your A matrix. So it will give me 0, 1, -1, 5. This is your A matrix. Your B matrix won't change and your C matrix also won't change. I think it's not given in the question. It's not given in the question. Okay, fine. So this is the linearized version of it. So I can write it as like a del of x1 dot, del of x2 dot. That is a linearized matrix. 0, 1, -1, 5, del x1, del x2 plus 0, 1 into u. So this is the linearized model of your system. Now, the third question, that is the important question, is they are asking us to find the poles of the linearized system. How to find the poles of the linearized system? Just simply the eigenvalue of del of A. That is this linearized matrix, right? So lambda I minus A equal to 0. So this will give me lambda 0 0 lambda minus of 0 1 minus 1 5. So that is lambda minus 1 1 lambda minus 5. Lambda square minus 5 lambda minus of minus 1 plus 1 equal to 0. So the poles should be around. I think this is not a whole equation. So minus b plus or minus we will use. Minus b plus or minus root of b square minus 4ac divided by 2a. 5 plus or minus root of 21 divided by 2. There's nothing we can do, right? 21 7 into 3. No, that's also 4. So 5 plus or minus root 21 by 2. These are poles. Since you don't have any negative signs here, is your pole stable or unstable? Can you type it in the chat box? Is the poles of the system is stable or unstable? Unstable. Everybody, please type it. Unstable, right? Okay. Okay. Then comes they're asking, okay, the another point rule is if you are asked to define a controller, you have to find the controllability matrix. You cannot just straight away go and find the controller, because even if it is not asking the question, it's your like rule to find the controllability matrix and see whether it is full rank or not. Okay, right. Now they are asking to find whether the system is controllable or not. So what is your linearized matrix? A equal to 0 1 minus 1 5. B is 0 comma 0 1. So what is controllability matrix will give B, A, B. If it is 3 cross 3, it will be A square B will also come. So B is 0 comma 1. If I do A, B, please don't switch the order. You won't get the answer. If I do A, B, A into B, this will give me 0, 1, my 0, 5. So it will be 1, 5. So your controllability matrix, sorry. So your controllability matrix has full rank, say, right? If you find the rank of the system, there is nothing to, there is that is scalable, that is repeatable. So your rank of your controllability matrix is full. So the system is controllable. Like we'll do observability matrix also just for practice, but it was not asked. So I'm randomly giving a C. Consider your C to be 1 1. So if you find the C matrix, the observability matrix O will be written as C and CA. It will be C A square, right? Until then C comma A power minus n will go. So since it is 2 cross 2, I'm leaving with CA. So this will give me 1 1. C into A will be 1 1 comma 0 1 minus 1 5. 1 into 0 0. Sorry, it will be like this: 1 0 minus 1 1 plus 5 6. So it will be minus 1 6, right? So your observability matrix is also a full rank matrix. If you find it, the rank would be equal to 2. Rank of O will be 2. So the system is observable. If it is 1, it is not observable. Anything less than the total number of rows or the order of the system is not observable, not controllable. Okay. The next question is, if the system is controllable, place its poles at -3, -5 using a state feedback control. U equal to minus kx, find k. Okay. Here you should know little bit. You should think about it. The actual system has a pole that is linearized. The actual system is non-linear. Now, then we linearize the system. Then we found this poles of the system lies in 5 plus or minus 21, root 21 divided by 2. That is something somewhere in the right hand side, somewhere here. We got this 5 plus root 21 by 2, 5 minus root 21 by 2. Okay. Somewhere in the right half of the explain we got it. So if you find the time response, or sorry, step input, if you give this step input to this system, how your response would be? Will it have overshoot? How will be the step response of the system? Anybody? Nobody knows. How will be the step response of the system? You don't know or you're not listening. Soma, Sonali, Kumar. Okay, it will be unstable, okay? Since the poles are in the right of the display. I think you are not in the meeting. Yeah, I was asking what will be the step response of the system. It would be unstable, like it increases exponentially. So I need the system, it's inherently unstable. I want to make the system stable, and the question reflects that they are requesting us to place the pole in -5 to -3. So instead of 5 plus root 21 comma 2 comma 5 minus root 21 by 2, they're asking us to keep the poles in -3, -5. Like here, we want to shift this poles here to here. So we have to design a controller such that u equal to minus k x. You have to decide this k so that it will bring these two poles here to the stable region. So by designing this pole placement controller, we are making an unstable system to behave like a stable system. This is the beauty of the pole placement controller. So if I have to place the poles at -3 to -5, what should be my k? That's what we are integrating now. For this, we need to write the required characteristic equation. So you know the pole locations are -3, -5, right? So I am writing it like this. So s plus 3, s plus 5 equal to 0. This is the actual characteristic equation that we need to bring. So I'm writing from the back end. So if my system should be like this, so then what is the characteristic equation? If my system has to have a pole at -3 and -5, then the characteristic equation is s plus 3 into s plus 5. Then I'm equating it to 0 and I'm finding the overall response like s square plus 8s plus 15 equal to 0. Now we are going to design a state feedback controller with which has the k1, k2, so that u equal to minus k into x. X is same. Now, since we know that the system after doing state feedback control will be a minus bk into x, y equal to cx, right? So I'm finding the a minus bk instead of the a matrix. So a minus bk would be a is 0, 1 minus 1, 5. 0, 1 minus 1, 5. We need to know the k, right? So I'm writing this. A minus b is 0, 1 and k is k1, k2. We don't know k1, k2. So this would be 0, 1 minus 1, 5 minus of k1 would be 0, k2, 0 plus k2. This is k1 plus k2. This is a minus bk. So if I want to find the poles of this equation that I can relate it with the characteristic equation, I have to find si minus a minus bk equal to 0. This gives me characteristic equation for this closed loop system, state feedback control. And I already got the characteristic equation of this. So by comparing these two, we will find the k1, k2 value, unknown value. That's what the idea is. So if I find the si minus a minus bk, I would need to know s0, 0, s minus of already. No, actually, this is wrong.
Yes, ma'am. It is 2 into 2 matrix.
Two, it should be 2 cross 2 matrix, right? Yeah.
Yes, ma'am.
Should be 0 and it should be 0. This will be k1, k2, right? Now it is right.
Yes, ma'am.
Already I matrix I wrote. Then this will be 0, 1, minus 1 minus k1, 5 minus k2. It is the whole this a minus bk matrix. So now this will be s and minus 1 minus k, sorry, plus, because there is a minus here. And this will be minus k plus k2. So this is the overall matrix. And finding the determinant of this will give me s into minus 5 plus k2 minus of minus 1 plus into 1 plus k1 equal to 0. So this will be minus 5s plus k2s plus 1 plus k1 equal to 0. Is it coming like this? Here I missed s, right? Say s minus 5. So if it is s minus 5, this is again wrong. So this will give me s square minus 5s plus k2s plus k1 plus 1 equal to 0. So s square plus k2 minus 5s plus 1 plus k1 equal to 0. This is a constant. So by comparing it against s square plus 8s plus 15 equal to 0. So this is equivalent to this and this is equivalent to this. So this will be k2 minus 5 equal to 8 then k2 equal to 13. 1 plus k1 equal to 15 then k1 equal to 14. So your k matrix is 14 comma 14 of 14 into 13. That's your k matrix. So this is how you find the state feedback control, pole placement controller, state feedback controller, both are same. This is how we will ask you to find the K matrix. This is a potential question. It can come in a comprehension examination. Giving a nonlinear system, we will ask you to find the linear first equilibrium point, linearized version for the linearized system, We will ask you to find the controllability or observability and to find the state feedback controller. This is one potential problem. Okay, that's it for today. You can ask questions if you have a doubt in the discourse and we'll answer.
Ma'am, in NSEM there will be pen paper, 50% CBT and 50% pen paper.
No, no, completely CBT only, computer based exam only. Yesterday we posted, no?
Okay, okay.
Okay, thanks.